Welcome to this Forge College Explainer. Now, if you were with us for our last session, you know we navigated the tricky waters of CPI error handling and CPI security. We made sure nobody could quietly sneak in and corrupt our shared state. But you know, that concrete CPI work surfaces a much deeper requirement. You absolutely have to know who actually owns your data at runtime. So today, we're transitioning into the strict, occasionally frustrating, but literally life-saving domain of Rust's memory management. Yes, we are talking about the infamous borrow checker, basically the micromanaging supervisor of the coding world.
Okay, let's take a really quick look at our master blueprint for today. We're going to cover everything from the basic, unbreakable rules of ownership down to the stack, heap, and pointers. Then we'll apply it all to borrowing Solana accounts, venture into the perilous, unsafe danger zone, and finally wrap it all up.
So let's kick things off with Section 1, Welcome to Memory Management, and meet the strict building inspector. Think of Rust's compiler, that notorious borrow checker was just mentioned, like a very, very strict building inspector. The absolute fundamental law of this land is ownership, and that just means every single piece of data has one and only one rightful owner at any given time. When ownership is transferred, we call it move semantics. The previous owner is completely cut off. They can no longer use that value. Imagine trying to build a house if two different contractors think they own the exact same physical blueprint, and both of them are trying to erase and redraw lines at the exact same time. It would be total chaos, right? Rust's ownership prevents this kind of dual mutable access right at the compiler level. This brings us nicely to Section 2, the rules of ownership, specifically shared versus exclusive borrows. Let's dive into how this building inspector actually handles sharing things, like your Solana account data. When we don't want to permanently hand over ownership, this is the golden rule of borrowing right here. You can have many readers checking the blueprint simultaneously. Those are your shared borrows. Or you can have exactly one writer making changes. That's your exclusive borrow. But listen, you can never, ever have both at the same time. The compiler simply won't allow it. It will reject your code outright. And honestly, this is exactly how Rust completely eliminates data races. The inspector also heavily scrutinizes something called lifetimes. These are annotations that specify exactly how long a borrow is valid. And in Solana, this is absolutely critical. You want to avoid holding on to an exclusive mutable borrow across a cross-program invocation boundary. Why? Well, because when you invoke another program, that program might secretly re-enter your code and modify the account data. If you were holding a borrow, assuming the data wouldn't change, your program would suddenly be left with a dangling, completely invalid reference. Now let's look at Section 3, Stack, Heap, and Pointers. Basically, our materials and zoning laws. We basically have three main zones for storing our building materials. First, the stack. Small, simple things like a U64 integer go on the stack. They are incredibly cheap to copy, so Rust just duplicates them safely whenever you pass them around. You don't even have to think about ownership headaches. Then we have the heap. Large account buffers, like a dynamically sized vector, live on the heap. Because these are bulky, assigning them to a new variable actually moves the ownership entirely, unless you specifically borrow them. And finally, we have raw pointers. These are basically the rebels without a cause. They have absolutely no borrow checking at all. But we'll get to those troublemakers in just a minute. Let's move on to Section 4, Borrowing Solana Accounts. How do we read the blueprint safely? When we're processing a Solana account, we generally follow a few core steps to keep the runtime happy. First, we borrow a short-lived shared slice of the data so we don't accidentally try to steal ownership of the buffer from the runtime itself. Second, we explicitly copy out small fields, like an 8-bit version number. Because it's tiny, making a copy cleanly avoids messy lifetime entanglements. Third, if we really need to do some heavy lifting, we create a local heap allocation that safely gets destroyed the moment our function ends. And fourth, well, sometimes we actually have to perform an unsafe zero-copy cast. Which naturally leads to a really crucial question. If this strict inspector keeps us perfectly safe, why in the world would we ever want to bypass these rules and write unsafe code? Welcome to Section 5, the unsafe danger zone. This is where we start demolishing load-bearing walls. You see, sometimes building inspectors just slow down construction way too much. We enter the danger zone of unsafe code for one main reason in Solana: raw, blistering performance. By using zero-copy deserialization, we bypass the normal safe allocations to read bytes directly.
but taking down a load-bearing wall to reach your data faster using raw pointers is incredibly risky. The compiler essentially takes off its hard hat, hands it directly to you, and says, "You're on your own, buddy." So the golden rule here is you must leave a clear safety note. It's a comment in your code, practically proving that you've manually checked memory sizes and alignments before you cast any raw bytes.
And here is a massive hidden pitfall of memory layout. Let's say your on-chain data is tightly packed to save space. Your counter variable might naturally start at byte offset 9, but Rust, trying to make memory access faster for your CPU, will automatically add alignment padding. Under Rust's standard C representation, that exact same counter actually gets pushed to start at offset 16. If you blindly do a zero-copy cast from your packed on-chain data directly into that Rust struct, you're going to read completely wrong offsets and silently corrupt your application. No warning, just broken data. To survive this danger zone without bringing the whole house down, you have to build your own guardrails. First, you must validate the minimum buffer length at runtime. Second, check the exact memory alignment. Third, it's highly recommended to verify a version byte or a magic header before you do anything else. And finally, you have to guarantee that zero mutable aliasing exists while you hold that reference. I'm serious, if you miss even one of these checks, your program will suffer from undefined behavior.
Well, we survived the danger zone, which brings us to Section 6, wrap up and next steps.
We've covered a ton of ground today, navigating from safe, cozy borrows all the way out into the wild west of raw pointers. So let's quickly recap how you can pass your final inspection. Treat ownership as your ultimate safety contract. When you're looking at account buffers, always prefer short-lived borrows and explicitly copy out the small fields to avoid tangling up your lifetimes. I'll say it again, never ever hold a mutable borrow across a CPI boundary. Rely on explicit parsing if layouts are mismatched, and please only use unsafe zero-copy casting when your performance absolute demands it and you perfectly control the layout. Oh, and always document those invariants. So I want to leave you with this final provocative thought. Are you ready to actually apply these exact memory principles? Because in our next lesson, applying ownership and memory principles to safe Rust code, we are going to get our hands dirty and refactor an existing Solana handler, completely converting its unsafe code into safer, cleaner abstractions. Thank you so much for joining this Forge College Explainer. I really hope this session helped solidify your understanding of Rust ownership, borrowing, and how memory truly behaves under the hood. Head on over to forge.college to learn more about this subject, dive into our next modules, and explore some other fascinating Web3 topics. See you next time!